So we've got Black Scholes equation, and the solution to Black Scholes equation that we're looking for will price an option. Of course, it doesn't. We're looking for we're looking for a formula, the value of the option as a function of the stock price and time, but it's also got to, at expiry, when time is equal to capital T, it's got to be the payoff function. This has to be the payoff function for the option with respect to stock. That's where we'll get that. That's why the linear combination of stock and time value of money cash didn't work last time. So here's our Black Scholes equation. What we're going to do then is we're going to do a series of substitutions. Just like you would solve an integral problem, you would do a substitution. We're going to do a series of substitutions and change this Black Scholes equation into a known problem, into the heat equation essentially, and we'll get something whose solution ends up involving the cumulative distribution function for the normal curve. Now, our first substitution then, so we're trying to transform this Black Scholes equation into something whose solution we already know. Our first substitution is, I've got V as a function of S and T, and I'm going to make it equal to then, this looks like a time value of money piece, times U of S and tau. So I'm replacing the time part with, well, tau, think of tau as the time left. So tau is equal to the expiry time minus the time it is now. So when tau is equal to 0, the time is capital T. So this payoff would be when tau is equal to 0. So I need to have, I need to do these derivatives. I'm using the notation that are from the book, but if I'm getting dV dt here, I'm going to have to do product rule. Derivative of the first is just going to pop out an R when I differentiate with respect to little t, times leave the u alone, plus leave the e to the minus rt. Now I need the derivative of this with respect to time. So this will be u sub t. I'm using that for my derivative. We'll do this part of the substitution when we make essentially time run backwards, because as little t goes up, time left goes down. And because we have our sort of initial condition at the payoff when tau is equal to 0, we want to start tau at 0 and go forward. Tau at 0 going forward is little t at big T going backwards. But anyway, let's do this substitution. The other stock derivatives, this part when I differentiate, so that's dV dt. If I want dV ds, well, there is no s in the first part, so we're just taking the partial derivative of u with respect to the stock. Now I'm mixing my notation here. The subscript u of s means the derivative of u with respect to s. This is a more convenient notation. And likewise then, our second derivative with respect to s is just going to be this with two s's. When I substitute that all in, so I'm putting these all in, let's put all those pieces in. So instead of, here I've got my dV dt. Here I've got my dV ds. Here I've got my second derivative, Oh, and we can sub in for what v is itself. Now, I'm just doing that u. What happens here is this piece and this piece cancel out. So let's get rid of them. Nice. Also, now every piece has an e to the rt stuck to it, equals 0. So let's just cancel that out, factor it out and cancel it out of each piece. Already our equation is simpler. If I could solve this equation for u, once I know what u is, then I can pop it in here and get what v is. Now let's take this t into consideration. Chain rule, if I was up here and I would differentiate, if I would differentiate something with respect to t, differentiate, I guess, anything with respect to t, that's the same thing as minus differentiating something with respect to tau. Remember, capital T is a constant. So I'm going to end up replacing then that du dt with minus du d tau. So this is going to become a minus du d tau, and I'm just going to bring it over to the other side since it's a minus. And then u differentiated with respect to tau. Now, here's my equation that has tau in it. So tau is running, starting at 0 at the payoff. A new substitution. The next substitution job is going to be to make these coefficients in front of the partial derivatives constant. So I'm going to think of the stock as e to the, well, let's see if we can use their so e to the squiggly epsilon, or in other words, another way to think about it is that's equal to the ln of the stock. Now I got to worry about these two derivatives are with respect to stock. So we've got a u when I differentiate with respect to stock. What does that do? Okay, we'll have to cut some of this because it's boring. Right now I've got u being a function of s and tau. And tau. I'm going to end up then, instead of writing s here, I'm going to write e to the squiggle. So when I differentiate with respect to squiggle, that'll be the derivative of u with respect to the first argument, which is like our s, so that'll be like u sub s times the derivative of s with respect to squiggle. Well, since it's e to the derivative of e to the x is just e to the x. So that's what we get if I differentiate u with respect to squiggle. It's the derivative of u with respect to s just times e to the squiggle. Well, now I need a second derivative as well. Okay, before we get our second derivative though, let's clean this up here, or let's solve for it. That's saying that u, the derivative, is equal to, so I'm basically solving for this piece here is equal to that. Or if I move this over to the other side, it just becomes a negative. Let's take this as our sort of starting point. Now I'm going to differentiate each side here with respect to s, because I need the uss to go into here. I need the second derivative of u with respect to s twice. So I'm taking this, both sides of this equation, and I'm going to differentiate with respect to s. Oh, up here, if I differentiate squiggle with respect to s, what do I get? Well, let's write that. That's going to be I'm just differentiating both sides of this thing with respect to s. That's just going to be straight 1 over s. And later on, if I want, I can make that s e to the squiggle effect. So let's keep that here. So now take this, differentiate both sides with respect to s. So I have to do product rule here. Derivative of this with respect to squiggle. Derivative of this with respect to squiggle minus e to the times the derivative of squiggle with respect to s. So that's the that's the derivative of the first piece. Leave the second alone. Plus leave the first alone. Times the derivative of the second, so I'm differentiating this with respect to s. So I'm on the second part. Leave the second part alone. No, leave the first alone, doing product. Now I got to differentiate. I have to differentiate this with respect to s. So it'll end up being derivative with respect to squiggle. Now times the derivative of squiggle with respect to s. So now I need another one of these. All right, so this is equal to the second derivative with respect to s. Yeah, never saw that before. So I need to put this piece in here, and I need to put this piece in here. So this is the partial differential equation. Now I'm going to replace these derivatives with respect to stock to the derivatives with respect to squiggle. So that's what I'm starting with. Instead of u sub s, I'm going to put this piece. Instead of u sub ss here, I'm going to put this piece. So now all my partial derivatives will be with respect to squiggle or with respect to time. Right now I'm working with the stock piece. Now let's take a look here. S is e to the squiggle, so e to the squiggle times e to the minus squiggle, those cancel out. Likewise, s squared would be e to the 2 squiggle, so when I distribute this s squared across the bracket, it's going to end up canceling those pieces. And what have we done? Well, there's all the coefficients in front of the partial derivatives are constant. That's the big payoff. That's what we've ended up accomplishing. And I guess I can collect on these two pieces here. There's two of these ones, so let's clean that up a little bit. Okay, so now we've collected over the three different kinds of partial derivatives. Our coefficients are all constant. R, risk-free rate of return, we get that from the 30-day T-bill. The sigma, we would get that as the standard deviation, the annualized standard deviation of the returns. We have all these values. Okay, so now I'm trying to find a function u, a function of squiggle and tau, that fits in this differential equation, this partial differential equation that satisfies that partial differential equation. And read this as, well, we would read this as the derivative of u with respect to squiggle, but let's say the first argument, the derivative of u with respect to the first argument. And this would be the derivative of u with respect to the second argument. The next substitution I'm going to do then is I'm going to let x equal to squiggle plus this bracket tau. What that means is, when I'm taking it, well, okay, what that means is that means epsilon is equal to x minus that bracket tau. So now there's a tau in the first argument and in the second argument. So when I differentiate this with respect to x, I want to differentiate this with respect to x, I get the derivative with respect to the first argument. I get the derivative with respect to the first argument times the derivative of the first argument with respect to x. And dx d, this thing is just 1. So differentiating with respect to x is the same thing as differentiating with respect to squiggle. So that means that differentiating with respect to squiggle twice is the same thing as differentiating with respect to x twice. So the x and the squiggle, the epsilon thing are straight swap. But differentiating with respect to tau, so I want to differentiate u with respect to tau. Now there's a tau in both arguments. So I'm going to need to do derivative of u with respect to the first argument times the derivative of the first argument with respect to tau, which is this piece. I'm just going to put it over here, but times the derivative of the argument with respect to tau, plus, doing chain rule I guess, the derivative of the outside function, the u, with respect to the second argument, times the derivative of the second argument with respect to tau. Well, the second argument is tau, so I mean I'll write it there, but it's just times 1. Okay, this looks funny because the way I've written it, I should be able to cancel these two pieces off. Well, I've written it in a casual way. This tau meant the derivative with respect to the second argument, what was in the second argument. So I shouldn't use that symbol. I need a holder. So I'm just going to put A to represent the second argument, the derivative with respect to the second argument, which is what this would be then, the derivative with respect to the second argument. So when I sub those pieces in, switching variables, these are all a straight swap out. But when I solve for the derivative with respect to the first argument, or the second argument, which I've got here as u sub a, that's equal to which means this piece, first argument, this piece and this piece cancel out. So now we're done. We get, well, no, we're not done. There's two x's there. This piece and this piece still cancel out, and we end up with this equation to solve. All right, but what have we done? If I can solve this equation that now has taus and x's in it, if I could solve that, then everywhere there's an x, I could put one of these pieces. Now it'll have squiggles and taus, and everywhere it has a squiggle, I'm going to put a ln s, and everywhere it has a tau, I'm going to put a t minus t. When I do that, then I've got, well, then I've got the u's, and everywhere there's a u, I'm going to put an e to the rt. Then that's going to give me. So I have to go through all of those back substitutions. But let's work on what we got to do now is solve this equation. Let's work on solving this equation. Undo. So we've got what looks like the heat equation. So we can start to use some of the borrowed mathematics from solving the heat equation. And the heat equation describes the flow of heat on a rod. So the heat will flow from hot areas on a rod down to cool areas on a rod. But if we think of the heat as the energy, and we add up all the energy on the rod at any time, it always equals a constant. It'll flow from hot to cold, but the total energy on the rod remains the same because we're thinking about this rod as being insulated. That's what this condition is giving me, that x is the distance on the rod. So at any time tau, if I sum up, integrate all the rod from minus infinity to plus infinity, I get a constant. More borrowed mathematics from a heat equation. We're going to express our u function as tau to the alpha, or tau to the a, let's say, times some function of eta, and our eta is going to be x minus x bar all divided by tau to the beta. Now I'm using all the Greek letters because this is the way it's done in the textbook. So I need to then sub my solution into this partial differential equation. So I need the derivative with respect to x twice. Well, when I differentiate this with respect to x, there's no x in that tau to the a, so it stays the same. If I differentiate with respect to x, it's going to be the derivative of f with respect to eta, so the derivative of f with respect to eta. Now, that's not a partial derivative, that's a regular, ordinary derivative, because f is just a function of that one variable, eta. Now I need the derivative of eta with respect to x. Well, the derivative of eta with respect to x is going to be just tau to the minus b. Now that's me differentiating once with respect to x, but I have to do this twice. So it's going to be the second derivative. And every time I differentiate, it throws out a tau to the minus beta, so there's out tau to the minus 2 beta. And that's going to equal to, now I need to differentiate this with respect to tau. There's taus here, and there's taus inside the eta, so I'm going to need to do product rule. Derivative of the first, when I differentiate that, the a comes down, subtract 1 from the exponent. So I've differentiated tau to the a. I've left the second piece alone. Now I just got to leave the first piece alone, the tau to the a. Now I'm differentiating this piece with respect to tau. So I'm going to get a derivative of f with respect to eta. I'm using chain rule on this. So the derivative of f with respect to eta. Now the derivative of eta with respect to tau. So think of that as tau to the minus b. A minus b is going to come down up front, a minus beta. And then I'm going to end up subtracting 1 from the exponent. But instead of writing that as subtracting 1 from the exponent, let me just make this as a 1 over tau to the minus 1. So I'm doing that so that I can just call this whole piece here again eta. So let's clean this up a little bit. I'm going to call this whole thing eta. And here I've got tau to the minus 1. Oh, that should be 1 over tau. That should just be tau here. 1 over tau. It's tau to the minus 1 up here. All right, what do we got? This is again eta. Let's put all our etas back. Now, oh, I've got it's like a second derivative here. What can we do? Oh, well, I haven't used this piece yet. If I integrate all over all the x's, so this has to equal a constant for all time, so it can't change as time goes on. Well, let's do a substitution then. I'm going to replace this piece with eta. So if eta is equal to what's d eta dx? D eta dx is tau to the minus b. So I'm doing just a plain vanilla substitution. I'm saying let that equal to, so therefore d eta dx is equal to, that'll just be 1 over tau to the b, or I'm just going to write it as tau to the minus b. Minus beta, I guess. I wish you wouldn't have used all those Greek letters. I think it's a pain in the ass, but all right. So that means that dx is equal to tau to the beta times d eta. So let's pop this in here. I'm doing my substitution, just a plain vanilla substitution. Since I've got tau, like tau's a common base, so I'm just going to bring those pieces together. Okay, this has to be a constant for all time, so it doesn't matter what tau I put in here. As tau goes to infinity, this still has to equal a constant. So there can't be any taus in here. The only way to get rid of that tau is to make A equal to minus beta. So that's our conclusion then, that A equals minus beta. That way this will just be tau to the 0, and it doesn't matter what time it is. It cancels out. So everywhere there's an A in here, I can put a minus beta. So let's go all the way down to our differentially, or our ordinary differential equation, and see if we can clean up here. A's are equal to minus betas. So that would be a minus beta. A minus beta. That'll be a minus beta. So now I only have one parameter here to worry about. Oh, I still got an A in here. Got to get rid of this A, minus beta. I can do some factoring here because I have tau to the minus beta minus 1 and tau to the minus beta minus 1. Let's clean this up here. What can I factor outside of that bracket? I can take that tau out, and I can take that minus beta out. Okay, so I've got a tau more common basis, so this will be tau to the minus 3 because I got minus 1 here and minus 2 there. Clean that up. There. So now what do you got? You got tau to the minus 1 or minus b minus 1 on this side, and tau to the minus 3 beta on this side. Beta on both sides. This equation has to be true for all time. So I need to be able to cancel the times off both sides, so that, well, if I couldn't cancel the times, the taus off both sides, then as time went on, one side would become a different number than the other side, and then they wouldn't be equal, but they are equal because it says so. So that means that minus 3 beta must be equal to minus beta minus 1. So beta's got to be a half. If beta's a half, then A is minus a half. So now I can go all the way up here to when I had my actual function, and now I know what these alphas and betas are. So we're saying that the only A's that work are B's got to be a half, so raise tau to the power of a half, that's a square root. And A's got to be minus a half, so this has got to be like 1 over the square root. So this is what our U is. All I don't know now is I don't know what F is. And it looks like so far I can choose any x prime I want. This x prime doesn't mean derivative. This x prime is just a number. Well, oh, if I go back up to here and I do that, now that I know the time has to cancel off each side, and I know that this b is a half. Oh, if I know that b is a half, then this half and this half cancel. So now, oh, now I've just got a regular second order differential equation that I can solve. So f as a function of eta f as a function of eta is equal to some number e to the power minus eta squared over 2 sigma squared. And since I get to choose what B is, I'm going to, this looks like the Gaussian curve, normal distribution curve, so I'm going to choose B so that the area underneath this thing from eta, from minus eta equal to minus infinity to eta equals plus infinity, I'm going to make sure that's a probability distribution. The area is equal to 1. I'm just going to make that a 2 pi under here. And I know what eta is supposed to be. It's supposed to be this. So now I'm just doing a bunch of back substitutions. Now I've got the u in terms of tau. Oh, I know what the tau is supposed to be. It's t minus t. Now we're getting rid of all these Greek letters. T minus t. I know what the sigma is. That I just get in the volatility of the stock. I don't know what x bar is, or x prime, but I do know what x is from way back here. Way back here. Way back where? X. X is equal to, okay. Let's get this. This is C xi. But what is that supposed to be? That's supposed to be ln S. So the ln of the stock plus this piece, ln of the stock plus that piece, and I know what tau is, t minus t. So now everywhere there's an x, I'm just going to put this expression all the way back here. I still don't know what x prime is. If I follow his convention, he just replaces, so if this is equal to x, then x prime just has an s prime in it. Right now I'm just leaving it as x. And then I would have what u is. What do I do with u? Oh, once I have u in terms of the stock and time, I just need to multiply it by time value of money. And that's V as a stock and time. Now, before we get too excited, we already had solutions for the Black Scholes equation. Pure stock worked and time value of money cash works, so this also works. But the reason why we had to go searching for something more complicated, this is certainly more complicated, is we need to find something such that when t goes to capital T, when small t goes to capital T, in other words when it expires, that this approaches the payoff. Well, already I see a problem here. If I make little t equal to big T, here I'm dividing by 0, up here in the exponent I'm dividing by 0. This makes e to the 0. That's fine. E to the 0 is 1. I can handle that. But these dividing by 0, I gotta worry about that. I gotta deal with that. So this is a solution. Well, we know that any linear combination is also a solution. So if I put some kind of a constant out front here, let's say, I don't know, k times that is also a solution to the Black Scholes equation. And if I make these k sub I, if I add two solutions together, so well, let's add more than two. Let's just add a bunch. If I add up a bunch of solutions and the only difference is that this I value changes, then that sum is also a solution. This x, I'm also going to make that, since I got to pick that, I'm going to make the x that I pick here, the x prime that I pick here, and the k sub I that I pick over there, those can change and this still is a solution. Well, now we're going to morph this sum into an integral. by making these k's really super close together. And I'm going to morph that so instead of doing a sum, I'm going to do an integral, and morphing a sum into an integral, something has to go to 0. If I'm doing this in calculus and I'm getting the area under the curve, it was the width of the rectangles that are going to 0. Well, what's going to 0 then in our case is the differences in the x primes going to 0. I still have these k's. These k's are now dependent on whatever x prime we're dealing with. So now I've got an integral that solves the equation. What I really need then is I need this limit. I need the limit when t goes to the expiry time. I need that limit of this function. Let's put that underneath. I need that to equal the payoff with respect to the stock. So that S is going to be what survives here as I take the limit as the time approaches expiry. Well, here's what I got to reach back into differential equations. Now this has been, admittedly, let's take a big break for a second. This has been a ton of math, and it's probably super exciting watching me do all this. I don't necessarily expect that that you will be able to, or that you will be required to. I know you won't be required to repeat all this, for grades or anything. But it's important that we understand how the Black Scholes formula at the end, the solutions to the Black Scholes. If you got your book in front of you, go look at page 200. That's where we're going. We're trying to build that chart. It's important that we understand the assumptions and how those formulas are produced, so that we can understand when we're allowed to use them, what assumptions went into building them. Okay, but let's try to make this as painless as possible. If I'm looking at this piece here, this piece of algebra here looks like the Dirac delta function. So what's that? If you remember from differential equations, you probably did this when you were looking at Laplace transforms. The Dirac delta function is a function that's 0 everywhere except for when it's infinity at x prime, the way this is set up. So if I were to integrate this, sum this over, this will be a definite integral, from minus infinity to plus infinity. I'm exploiting that property of the Dirac delta function that you would have exploited when you got its Laplace transform. If I sum this up, then this should just equal to the k at the x prime. So this should equal to that function k at the particular x that we're looking at, x prime that we're looking at. All right, so what does that mean for us? Well, that means that now I know what I should make k. I should make it the payoff. So I should make this the payoff function. Now I'm going to jump ahead of myself here at a stock, and I'm going to call that S prime. So the payoff, so if it was a call option, I know what this graph looks like. If it was a call option, it would be 0 until it hit the X exercise price, and then it would go up with a slope of 1. So I got to go all the way back up here where we were defining x. Oh, there's a lot of algebra, eh? Man, where do we even put that? Where we defined x, here it is. Okay, I'll make it big again. But the nice thing is that, look, dx prime is just going to be 1 over s prime ds prime. So I'm swapping this piece out here. Now, what do you got? Oh, I'm integrating over the stock price s. The stock price can never be negative, so I don't need to go to negative infinity. I can start at 0. So I haven't said what x prime was yet. I'm going to call x prime the ln of s prime, so that dx prime is just ds prime over ds. Then this is not here. I don't need that extra piece. And I'm squaring this. If I square the denominator of this piece in here, that'll just put a t minus t on the bottom. Now I've squared that. Alright, we're at the stage where we're about to say, so what's going on here? This, we're done actually. This is the formula. Formula 8.7 in the text. That all I have to do is put in the actual payoff as a function of s prime, integrate this from 0 to infinity. Okay, that's easier said than done. But once I integrate this from 0 to infinity, I'll end up getting a formula that has s in it. The s without a prime is right up here. The s without a prime doesn't get integrated out. The s with a prime, that s with a prime is on the bottom here, that s with a prime gets integrated out, and only this s is left over. The t doesn't get integrated out, and I end up getting this formula, the formula that prices an option as a function of its payoff. We're going to have to wait until the next, you're going to take a break, take a look at what it does in the how it's written in the book. In the book, they ln of s minus ln of s prime, they put that into one fraction. So the book will do this to try and make it even simpler. But this ends up being, we have to evaluate this integral. This is the big payoff here that we did. Okay, let's take a break.